Okay, so we'll just ask a few questions about congestion, and then see if you have any questions. If anybody has any preference to any material we should go over, ready for tomorrow's test. And if you leave it to me, then maybe we'll do one exercise of every topic that we've done, like error detection, the CRC, the Hamming code, and the sliding window protocol, the go back in, and the selective repeat. And what else did we do? And the routing, the Dijkstras algorithm, finding the shortest route. And finally, what else did we do? In the signaling bit, the scrambling technique. So these are, at least those are 5 or 6 topics that are possible topics for questions for an exam or a test, and that you should be quite aware of how to do those mechanisms or those calculations, as well as obviously the theoretical kind of answers and explanations and advantages and disadvantages and of how things operate. But at least, you know, those, even if not for tomorrow's test, but they're definitely good revision for the final exam test. But tomorrow's test will also have a number of those at least, between error detection, flow control, scrambling, and routing, Dijkstra's algorithm. So congestion is not going to be on tomorrow's test, right? But we've covered it last week. Just we always go over and ask a few questions just to make sure we are okay with it. So what are we going to start with? Who could tell me what's meant by congestion? What is actual congestion? Anybody want to describe or let me know what congestion is? And then yeah? You know what congestion is?
Router has too many packets to send and cancel.
Okay. So, yeah, it's fine, but not one feature of congestion is not limited to one router or two. That's, if one of the questions normally that comes up, what's the difference between congestion and flow control? Anybody know what that, can anybody give me a difference between congestion and flow control? You wanna have a go?
Is it like congestion can affect the whole server kind of thing, and then flow control is more?
Yeah, this is one of the major differences between flow control and congestion, is that flow control affects 2 devices. Congestion affects an area in a network or the entire network. An area is like a few routers and few number of devices. It's communication. They all deal with moving packets. But congestion, just in general, in a network, congestion means there are more packets, more than the network can handle, or in an area of a network, more than that area of the network can handle. So that's what congestion is generally. Flow control is having flow of packets problem between 2 devices. And it's only usually caused by faster sender and a slower receiver. In congestion, it's caused by fast sender sending fast data into the network that going through the network to the other recipients but the network can't move it fast enough to the recipient. So you end up having slowly, more traffic comes in than the traffic that leaves. And that's what traffic ends up building up, packets end up building up in the network or in parts of the network. And that's what congestion is. So how could congestion be prevented? Any mechanisms or tools used for prevention, not solving the problem of congestion after it happens? Any suggestions? The idea of prevention of congestion.
The choking,
Choke packet.
Yeah.
Okay, choke packet is more, yeah. You know how the choke packet operates? How does it work?
Just one node that should be sent doesn't show.
Does it, when you say warn them, did you say warn? Warn the senders to reduce, is that a recommendation or is it a command in choke packet? The idea? Yeah? It's a command. In the case of the choke packet, routers will normally recommend, in fact, it's compulsory recommendation, that the other packet tell these packets to reduce your traffic that you are sending by a certain amount, normally 25%. And then packets must respond to that. And if they receive another choke packet, it could mean another 25% reduction. And that reduces the amount of traffic coming into a network. Okay, so, and that normally happens, a packet or the router will send choke packet once it starts noticing signs of congestion happening. It knows the number of packets are increasing in the network. And how do they know? How does a router know maybe there's congestion around that router? Any idea how a router knows that there's congestion is beginning to build up? Any ideas? Any suggestions? No. Okay, normally routers keep an eye on the amount of memory they have. The total memory, the free memory, and what's part that's full of the memory. And usually there is a ratio, a certain percentage. If that's reached, if a router notices, for example, 85% of its memory is full, then it might say, okay, I'm getting too much traffic. I have too many packets sitting in my memory. They should be leaving, but maybe they can't leave because the other routers are full. They can't accept any more packets. And therefore, that's a sign of congestion beginning to build up. Packets are beginning to build up and congestion is starting to form. And in order to stop it from forming, as the choke packet is a way of error prevention. So congestion prevention, to prevent congestion before it actually materializes, before it happens. But we can see signs of it are beginning to form. The next one is called the bit warning. What's the difference between bit warning and choke packets? Bit warning? Is that what it's called? Yeah? Okay, just a bit closer here.
Bit warning is a suggestion rather than, well, not a suggestion, it's like you don't have to follow it. Yeah, recommendation. You don't have to do it.
Okay, and when would the routers issue a bit warning? Again, if it notices that there's a possibility of congestion, or congestion is starting to form, and it would know it by watching out the memory, its memory. And the more, obviously, the more memory, the less likely congestion is going to happen. But when things slow down, doesn't matter how much memory you have, it's going to fill up. Okay, well, the leaky bucket algorithm. Can you tell us anything about it? One statement about the leaky or the leaking bucket algorithm. Anybody has one statement to say? One thing to say about the leaky bucket algorithm? Attendance is working, so take your attendance, guys, please. Register your attendance. The leaky bucket algorithm is a technique that's used to give the indication that if there's too much traffic arrives to the network in a very short time, that it's absorbed by the router on the edge of that network, takes as much of it as it can, and then forward it to the network at a much reduced rate. For example, in this simple example here, if you get this much traffic, 12 million bits in 2 seconds, then hold on to it, store it, and send it into the network over a period of 10 seconds at the rate of 3 million bits per second, or something to that effect. So you get huge amount of traffic. If it goes into the network, it's going to cause congestion. It's like in a city. You know, at one motorway, it's too much traffic, we'll then have a big space of car park. Everybody goes in there and then release them at a lesser rate. So it'll take longer to travel, but at least they will not cause a congestion. Remember, every network, the congestion happens because there's a lot of traffic comes into the network and a lot of traffic leaves it. As long as the amount of traffic coming is the same as the amount of traffic leaving, then there'll be no congestion. But if the amount of traffic that comes into a network is more than the traffic leaving, then that's when more traffic stays in the network. And the more they stay in the network, the more likely we're going to have congestion. It's like cars, very much like the traffic in a city. Every day, every city, the more traffic comes into the city, but also hopefully some will leave. But if they don't leave, they'll take the spaces on streets, on roads. In fact, in most cities in Europe, especially Paris, they say if all the cars move at the same time in Paris in one day, they'll have no area to move on the street. They'll all stop because they'll fill the street areas. And many cities try to find solutions to that, and their solutions sometimes, again in Paris, as far as I know, is that cars that are registered in odd number of years, they move on Saturday or Monday, Wednesday, and Thursday. Are there any French people here? Is this correct or true or not? I've heard that only half of the cars are allowed to move in any day, based on what day registration, what your registration number is. You can move on a Monday or a Tuesday or a Wednesday. And if you move at the wrong day, you get fined for it. So, but anyway, that's one way of reducing traffic in a place. But on computer networks, we just don't allow the traffic come in, but it's one way of doing it. Or, just let the traffic that comes in at a reasonable rate that we can deal with it and process it and leave it and allow it to move. Because remember, especially in computer traffic, the network is there, it gets traffic from one end that's heading to the other end most of the time. Users who generate traffic, and usually users send traffic to other users through the network. So traffic always comes into the network and heading out of the network. But if it's slow to leave, then we start building more traffic in the network. And we can hold on to traffic in the network in memory of all the routers. But when memories of routers fill up, then any more traffic that comes in, it's discarded. And that gets worse. When it's discarded and not received by the receiver, it might be retransmitted again, and we start getting duplicate amounts of traffic into the network. So these are some of the techniques that deal with it. Either the warning bit or the router at the edge tell the senders, hey, we're experiencing traffic, please slow down. That's called the warning bit. So every computer that sends traffic to the network, and the router sends you back acknowledgement, and in the header of every packet there is a warning bit. If it's switched on, it means, hey, the traffic is getting heavy, try to slow down. But it's not compulsory to slow down. So if they don't slow down, then more likely the traffic is going to cause a congestion. Now we get into the compulsory bit, and that's the choke packet. The choking packet is a command to reduce your traffic. So choke packet is a packet that the router sends to the sender, to the device that's sending traffic into the network, to say, cut down your traffic by 25%, and they must reduce their traffic. And sometimes it's not the edge router that notices that the congestion. Another router down along the way into the center of the network somewhere. But they also now can send what they call step-by-step or hub-by-hub choke packet. That means one router sends it to that user up there, but has to go through another router. That router is also required to reduce its traffic, and the router passes to the next router. So this kind of choke packet, the hub by hub, every router passes through is also demanded to reduce its traffic until it reaches the final, the device that's really generating the traffic, and it should be reducing its traffic. So these are kind of techniques after a traffic has already started developing. But if it hasn't developed, this technique, the leaky bucket algorithm, is a technique that's used to prevent congestion before it happens. So by not letting too much traffic into the network, by holding onto the traffic at the memory of the devices at the gate of the network, and then releasing it into the network at smaller, reduced rate, it will prevent congestion. And the leaky bucket as well has its own problems. Like if we have a router at the edge, the gateway, and it gets too much traffic, sometimes it doesn't have enough memory to hold all the traffic coming to it. And they have the problem of overflow. So you start losing data before it actually enters the network. So they improved this algorithm that's known as the leaky bucket by something called the token bucket. The token bucket is also a leaking bucket, but it doesn't just accept any data from users. Users cannot send it data. It actually generates tokens, like permissions to send me data. So if it knows it has, say, 10 million bytes, it might issue 10 tokens of 1 million byte each. So if you have data to send me, come and request a token. Then I'll send you a token, then you can send me 1 million byte. But if I don't send you a token from full, I will not forward you the token, and therefore you keep your data before sending it. So just a way of controlling the senders from actually don't send at all unless we can handle it. So if it can be handled, then you'll receive the token. So that's known as the leaky token algorithm. And finally, the question is usually flow control. Does flow control controls congestion as well? If every machine, every router that talks to somebody who is sending us data into the network, we have a flow control. You know, the sliding window protocol that normally tell that sender to slow down until, you know, for example, window size 5, then the sender can only send you 5 frames and stops until you send them forward and deal with them and then ask for the next 5 frames. So does that help or does that stop congestion from happening in a network? What do you think, guys? See, congestion is having too many packets coming in a short time. So by using sliding window protocol, could sliding window protocol be enough tool to stop the forming of congestion in the network? Anybody wants to comment, even if it's a wrong comment? All comments are welcomed at this stage. What do you think? Sorry. It wouldn't be enough to stop it. Why not?
Just because you had one, like the flow control of one wouldn't be enough for the next one kind of thing. So one will pile up with information because it's able to receive it fast if it wants to, but then that machine itself will get congestion because it has to wait on the slow send out that it has to the next machine.
Okay. Anybody else wants to add anything? What about if the router that's on the edge of the network is actually faster than the machine that's sending? Would flow control still slow the slower sender, even though it's a fast sender, but it's not as fast as the receiver? How does flow control work? Can you tell me, how does the flow control the general idea? So what does it solve? What is the flow control problem? A more precise explanation of the flow control problem. What's a flow control problem? When does it happen? So when we have a faster sender and a slower receiver. So that's what flow control problem is. If we have a faster sender and slower receiver, then we have a flow control problem. And the sliding window protocol will slow the faster sender enough for the receiver to be able to deal with it. But if the sender is fast, but not faster than the receiver, because the receiver is also fast at the edge of a network, then it will keep on taking, it will not slow down the fast sender, even because it's not faster than the actual machine. But the rest of them will slow down the network. So flow control, it works a lot of the times when the sender is faster. When the sender is not faster, but the sender and the receiver are fast, they will allow a lot of traffic to go through. The sender will not be slowed down. So sometimes we don't slow them down, but our network cannot handle that. And that's where congestion can happen. So in general, flow control would contribute, would help reduce congestion, but it will not fully solve it. You need other tools to, in fact, solve the flow of the congestion problem. But it's a positive kind of protocol, flow control. It solves the flow control problem, and it will not be a negative. It will not have a negative effect on congestion. It will have a positive effect, but not the one that will sort it and solve it forever. Okay. Right, the next one. Any preferences, guys, to what we go through? You have the different options. We have flow control, we have CRC error detection system, we have Hamming code, and we have Dijkstras algorithm for shortest route. Any preferences, or will I make the choices? Hamming code? I didn't.
Scrambling.
Okay, yeah, scrambling. Yep. Anybody knows the rules for scrambling? First, what's scrambling used for? Scrambling, what is it used for? What's the main purpose for using the scrambling technique? Thank you. Yeah. If you're sending data, normally in the polar AMI coding technique, the polar AMI takes the ones and alternate them between +5 and -5. But zeros, it leaves them at 0 voltage. Problems can happen between a sender or receiver if there is no change in the sign, in the signal. And that can happen in the polar AMI if we have long string of zeros. So if you have 10 or 20 or 30 zeros of bits of zeros, then we just have a zero signal. Anytime you have just a zero signal, or just +5 signal or plus minus signal, anytime the signal does not change its value, we call that direct current. It's like you're just sending +5 all the time or 0 all the time. And one way for the receiver to synchronize itself with the sender, if there is a change, if it senses there is a change of voltage from +5 to -5 or to 0, If it finds a change, it will line itself up with that change. But if there's no change for a long time, the sender and the receiver will synchronize, go out of sync. They slip out of the bits boundaries. So every time this guy sends a bit, this guy should read a bit. That's a bit, another bit. But sometimes they get out of the timing of the bit. So this guy sends a bit, and this one, and sends the second one when this guy only reads one, because this one takes longer time to read. Because they're not lined up, they're not synchronized. And what caused them to be out of sync if we have continuous electric power in the signal, or the power of the signal is continuous. So we should always swap them. So the problem with signals is that if there is a continuous zero, we know the polar what you call it, the encoding technique is that alternates. But anytime it finds ones, it goes +5. A 0 goes to 0, and then another one goes to -5, another one +5. Anytime it finds a 1, it will alternate. So there's no problem if you have a long string of ones. It just keeps swapping between +5, -5, +5. So the receiver is always in sync with the sender. But if you have a long string of zeros, that's the problem. So now scrambling is used just for this purpose. If there's a long string of zeros, it will force some sort of swapping in such a way, in a calculated way, in a code that the receiver knows, oh, this code is just scrambling, it just means zeros. So even though it kept the receiver in synchronization, but it's still telling it that we are only transferring zeros, even though we are getting plus and -5, they might look like a 1, but they are not ones. They're all long string of zeros. That's in a very special code. And the code is based on rules, and that's what you might be asked, is to how do we convert that long string of zeros, what the code you convert it into. That's what scrambling is. So the receiver will know, oh, this is a code, this is not ones and zeros, it's all zeros, and replace them with that. And normally there are two techniques. I'll probably, will one of you open up whatever your notes and get us the rules for converting those. So this is, let me get a marker. The question could be something like this. For example, if you are told, normally you need to have some lining. If in an exam you get the question for scrambling, you must use vertical lines. Otherwise, it may not be clear where the end of each boundary is. So let's say you have those 3 ones and then followed by zeros. 1, 2, 3, 4. Oh, there should be maybe 2. 1 here and 1 there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 1. There. Let's say we have this string of bits that we need to transfer. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 zeros, just so 10 zeros. We have 3 ones, 10 zeros, and then 2 ones. All right, we're going to send them. Normally, we'll use the polar AMI. That is, you're alternating the ones between +5 and -5. And the 0 is there. So normally, this is important to know, and you're told this is the start of the transmission. You could be told, you could be given a diagram where it shows where the first bit 1 is. Is it a +5 or -5? Or you could be just told the first bit has a +5 or -5. So you need to know, it's important to know how many ones and what's the first value is, a plus or a minus, whether in a diagram or in words. So let's say this is what we are told, and this is the signal that's being moved. So the signal starts +5 at 1. The next one, anybody knows what the next one is? It's -5. The next one is +5. Now we have 10 zeros. Now there are two techniques used in scrambling. One, anybody remembers the names? No, before that. One technique uses 4 bits of zeros and another one uses 8 bits of zeros. The 8 bit is known as the B8Z, is it? And the 4 bit? This is the technique used in Canada and North America. And the 8, or which technique is used in America? It's the 8 bit, isn't it? Anybody knows? Yeah. So this is Canada and US, and this one is the one in Europe. So what does that mean? It means for Europe, now let's go to the American one, the B8Z. It looks for any 8 bits. If there are 8 bits, it will convert them, scramble them. So it will look 1, 2, 3. There are 10 here. So we're going to scramble up to this point, up to this 0. So what is the rule? Anybody finds the rule in there for the 8Z? Yeah, what's the rule? Does it say how many ones before you or before that? Anybody has the rule? Okay, I think they just look at the last 1 bit and they operate by going 3 zeros, did you say?
Yeah.
Yes.
Followed by a violation. A violation, the normal operation, if there is one, if the last one here was positive, then we'll go for negative. But a violation will violate that rule. So instead of going to negative, we'll go back to positive. So there, we made a violation. Followed by, anybody who is it a 0 or a normal operation? A normal operation, that's called the B. So normally, we'd write it, we say, you put 3 zeros to replace it, followed by a violation, followed by a B, which is a normal operation, that's bipolar. So this is, the B stands for bipolar, that means bipolar, that means to use the positive pole and the negative pole, bipolar. We choose the two of them at alternating. So now we go positive and then followed by 1 0.
1 0. Then B.
Then a B, which is
Violation.
a violation. So a violation, we go down instead of normal operation, followed by a normal operation, which is up, and that's it. Right? Is that it?
Yes.
So that's using the 8, depending on this one here, the last one before the string of zeros. If it's positive, then you'll end up going upward. So if you learn just one technique, so this one goes 0, another violation, and a B. So that's one way of doing it. 0, 0, 0, violation, normal operation or bipolar, 0, a violation, and a B. So if the receiver receives this code, 3 zeros followed by a violation, followed by a bipolar, 0 violation, the receiver will say, oh, this is special code. The moment it receives a violation, the first violation it receives, they'll say, oh, hold on, that's a violation, that's an error. Hold on, maybe it's not an error, maybe it's the special code. So it follows it and finds it matches the code. That means it's not an error, it was intentionally introduced by the sender. It will remove those 8 bits in the receiver machine and put 8 zeros. And this way, we're able to transfer 8 zeros to the receiver, but we did not leave the signal to go constant for the distance of 8 zeros. We were able to introduce those pluses and minuses, so the receiver will line itself with the sender, and therefore we do not get the synchronization problem that we used to have. So that's if the technique was the B8Z. Now what if it was the other technique? The North America technique uses, it doesn't go as far as, or the European technique, sorry, the other one, whichever one, it goes 4 bits. It takes 4 bits. Every 4 bits, deal with them, and then looks at the next 4 bits, deal with them. So remember, what happens here? You need to finish the signal here first. There's still 2 zeros left. 2 zeros don't require scrambling because they're not 8 in this. So we treat them normal. The zeros, they get no sign. And then the next one, where does the next one go here?
-5.
Minus, because the last one was a +5. So remember, if this was the other way around, so this is the answer that was expected from you. If this was a question, remember, if there was 3 ones and they're starting by plus, if it was starting by negative, if they actually look at the last one before the 80, is it a +1 or a -1? And work based on that. They give a violation because of that. Now let's do the other 4 bits. If we got the same bits, but now we're gonna scramble them based on the 4-bit technique. But we still have the same one here, +5. We start with +5 and -5. And then another +5. And now, what are we gonna do with this? So, in this technique, it says count. This is a little bit more kind of tedious than the other one. The last one, the one with the 8-bit, you just look at the 1 bit before the zeros. Is it 1 or is it plus or minus? So if you have 80, we look at the last bit before the 80. Was it a plus or minus? And that's what will cause this to form. You'll always violate against it. So if it's plus, you'll go plus, that's a violation. If it was negative, you'll go negative here. But with the other bits, with the 4-bit technique, you have another question to ask. Not just what value it was, the last one. No, how many ones there were since the last scrambling? So I told you here that we just started transmission here. That means there was no scrambling before us. So now we're going to start scrambling. So how many bits were there before the last scramble? How many real bits that have the value 1? And here we have 3. So it depends. Whether it's an odd number or an even number, it's important to know. So in this case, there are 3 ones. That's an odd number. And the odd number, it means replace every 4 zeros with 3 zeros and a violation. And if it was an even number, replace it by a violation and 2 zeros and another violation. So this is the rule that you need to follow. So you look, if we're asking for the scrambling of 4 zeros, that's a BHR something technique, then you count how many ones were there before the last violation. There's either going to be an even number or an odd number. If it's an even number, the way I remember it, if it's an even number, we're going to have the solution that has even number of zeros, which is 2. And if it's an odd number, we're going to replace the 4 zeros with 3 zeros and a violation, with an odd number of zeros. So now we had 3 ones. That means we're going to go for the odd one, which means we're going to have 1, 2, 3 zeros, followed by a violation which goes like this. Now, we have 4 more zeros. We need to look, how many ones did we have after the last violation? after the last scrambling. And we had no ones. There's no one. This is a violation. This is scrambling. Since this scrambling, did we have any ones? We have a zero number of ones. That's we consider that an even number, a zero. So an even number, that means go for a violation. We apply this, 2 zeros and another violation. If we had a 1 after this violation followed by 4 zeros, then that would be an odd one. But this one here, this -5 or this -5 will not be considered a 1. They will consider part of the scrambling. After this, if we had another bit, normally 1 bit or 2, then they'll determine whether we go for odd or even. Okay, so this is the scrambling. I have a quick one. I'll give you an example. Imagine if we had this number. You had 1, 1, 0, 0, 0, 0, 4 zeros. 1, 1, 2, 3, 4. And that's it, 1, 1. And this was a +5. This first one was a +5. Can you scramble this, please, using the 4-bit technique, scrambling technique? I'd like you to maybe just draw lines, vertical lines that separates the bits. Try to have the lines as equal as you can. In a test, you must have those vertical lines because we'll follow them, you and I will follow them to show me where you mean, where's the bit. Okay, this is +5, this is -5. The first one is a +5. Can you draw this, including the scrambling? Go on, have a go. You don't have to, If you're doing something else, that's okay. This is for your benefit for tomorrow, so. A piece of paper, with pleasure. Rather than seeing you sit and doing nothing, you like a pen as well. Vertically, whatever way. But just have quick vertical lines to indicate the boundaries between bits.
Why are you talking to me?
There's 1 before the 0, so after the 0, after the 1, the 1 has to be done. It's just after that. Is everybody finished here? No, the 1, 1. now you have a violation followed by 2 zeros because they are even number of one. Once again, no, okay, no,
Yes.
yeah, that's the one. Oh, this is the one, we should start the first one, is the, the first one is a plus, and then minus. And then you have 4 zeros, how do you replace it? It's 1, 2, 2 ones before this rounding. That's an even number of ones, that means you go with violation 2 zero 1 violation. So you do violation 2 zero 1 violation. Now we have, this one with 4, no, and 1. You go 1 and then now we have 4 zeros. How many ones since the last violation? You only know. It's not a number. It's not 3 zeros. Okay, check the rule. Okay, guys. The rule says, right, and the question here says, the first one has a +5. The next one is -5. That's how this is called normal operation. Now we have 4 zeros. We're gonna introduce the code instead of 4 zeros. It says, check how many ones before this violation and since the last scrambling. There are 2. That's an even number. If it's even, go with normal operation, 2 zeros and a violation. So normal operation brings us up because the last one was minus, 2 zeros and a violation. Here we go. That's how we replace the 4 zeros. Now we have a normal one. If this was a plus, the normal operation is minus. What happened there? The internet was lost.
Turn off.
I don't know what got turned off.
It's the left, the thing you were projecting there is on.
So are we okay now? No, there's no. It's more than just turning off. It's I'm not getting anything from it.
I was. Yes, it's so small.
I had to sign in.
Yeah.
You should do the admin. And then first I had to click on it, like click the file.
Yeah, we'll stick that.
And then close password. Okay, the BIOS is like password. Oh, nice. Go back to that. It's like, change the password. I know the brain space remember everything that's at the same time. That's why we have like teaching software. Exactly.
All right, back to operation. So now we have 4 more zeros to scramble, and we need to look at how many ones.
Why does that happen? It happens everywhere. Review. Like, wait, what? If they do, they should be fast. They don't want it so fast. You're not fucking like, you know, it's always has temperature or else they just like, it's not like a little bit. That's fun. Like I get it's like Irish, but that's like culture Irish. Guys, this is guys. You know, it's like I guess. He's joke. It's like never stabbed the keeper, but it's like so the thing is first, your backspace to do that space 2 years.
All right, I think we're back. Operation. All right, so this is the 4-bit operation. Scrambling 4 zeros. We see how many ones there were before the 4 zeros. In the case of an even one, we go for B00 and a violation. So the B is normal operation, 00 and a violation. And then we have a normal one that goes into the last one, the last value of the signal is +5, this goes into -5. Now we have 4 zeros. We see how many ones there are since the last scrambling. There's one. One, that's an odd number. And in the case of odd number, we go with 3 zeros and a V and a violation. So it's 1, 2, 3, these are 3 zeros and a violation. And then we could carry on with the other ones. So normal one and down. So this is the 2 scrambling methods that are used. Anything else? So shall we try the
sign off.
Let's try Dijkstra's algorithm for finding out the shortest route to a router. So let's say you got this, yes? You have a question there? You want your hand back? Yeah. Maybe the question reads something about the last. Maybe the question is slightly different. What is the question?
Because he is actually.
Okay, guys. Now let's try the Dijkstra's algorithm. The last time we done is for find the shortest route to router A. Now let's find the shortest route to router G. If you are asked, given a network, and you are told, can you find the shortest route to a router G from all locations? We should produce the following table. You start by first plotting all the routers that are there, and we put them in this sequence A, B, C, D, E, F, G, up to the end. Now we want to work out for G, right? This is the one we want to work out the best route or the shortest route to router G. So you start with G. That's the one you start with. And you say, if you are in G and you want to go to G, what's the cost? 0. It can't be shorter than that. Now, check all the routes from every router to G now. I don't know if you remember the way Dijkstra's algorithm works. It says, look at your neighbors. And G has 3 neighbors, and find out the best neighbor, the shortest neighbor. Anyone that you do not have a direct link with, put a maximum infinity. So we don't have a direct link with G, either from A, B, or C. So A, B, or C, we'll hit them with infinity. From D, what's the cost from D to reach G? It's 1. And it's straight through G. So I'm going to use a different marker here, maybe. 1 through G. And this one doesn't work well. Okay, maybe the pen. See if the pen works well. From E, it's 3, and it's also going straight through G. Can you see this color? No, barely. And from F, it's 1, and it's going through G. So 1, 3, or 1. For now, this is the best, this is the main route. Now we're going to find the next best element in the route. What you do, you look at the line and say, which one of these has the smallest value? And that would be your next point. So we have a D or an E, F. They both have 1. We can pick any one of them. Okay, D. Right, D. So we bring D down. It's 1 to G, and we put around this circle. So that's the next. That now D is on the main route, on the shortest route to G. Remember, we're going to G now, the shortest route. Now, calculate what is the shortest route from all the neighbors to D now. Forget about G, we're finished with G. So D has direct neighbors who are A, C, and E. It doesn't have B or F. So for B, we give it infinity, and F, it already has a value, we bring it as it is, no change. But it has direct link. Now I better write D here. So D is the next device. Now, from A going to D, now we're working to D, heading to G, what's the total cost? 3. So from A it costs 3 to reach G, but we're going through D. The next one, C, going through D. And remember, if you find 3, it's less than the previous value, we'll take it. If the previous value is shorter, we'll keep the previous value. Now, the next one, from C to G, going through D. 3 and 1 is 4. It's less than infinity, so we'll go for it as well. So it's 4D. The next one is E. To go from E to G, it costs 3. And it's through D. But we already had 3G. We can't find any smaller. So we leave the previous one. Okay? If you find a smaller value, you take it. If not, you leave the last value that was there. If the last value is smaller or is the same, leave it. Now you look at those and see which one has the smallest cost. And we have 2 of them that have So F, sorry. Yeah. So now we bring F becomes the next item in the shortest routing sequence. And we write F here. So the shortest sequence is to go from F. We'll follow it later on, we'll see. So F, it goes 1G. Now you'll have to check all these remaining neighbors. Forget about the ones we've already done. D and G are done. So check the rest of them. A, how much does A take? If it's direct neighbor of F, if it's not, just keep the same value. F has 3 direct neighbors, G, E, and B. So G is already done, so we're going to consider E and B only. Now, E and B, let's start with B. B to reach to F, and then from F to G, the total cost is 4. But remember, the mistake some students do, they just say, okay, from B to F, it's 3. It's not to B, we want to go the total. Or you can say, okay, to go to F, it's 3 plus 1 to bring us to G, that's 4. And that's 4 going through F. The other one was, the other neighbor is E. That's 1 and 1 is 2. So it's 2F again. Now, those A and C are not neighbors of F, and therefore we just bring them down as they are, with the values that they have. This one has 3D, and this one has 4D. Now, out of those neighbors, remaining neighbors, which one is the best, other than F? So we have this one here, E, which has 2F. So we bring, this is now going to be the next, E is the next value. We write it there. Now let's work out any direct neighbor to E that has not been calculated. E has F and G, we've already done F and G. It has D, we've already finished with D, so it only has B and C. From B to go to G, it costs 4 through E. From B, it costs, it's already 4, we leave the older one, 4F, because it's not smaller. The next one is C, I think, yeah. The other neighbor is.
Can B not be 3?
Sorry, where?
Can B not go from B to E?
It should, if it's 3, or did I make a mistake? Where?
No,
From
you just
B.
picked a different route, so it's.
No,
So
no,
if you
okay.
do B,
B.
to F to G.
See, now we have to go through E, right?
Yeah.
To go through E, it costs you 4.
Can you not go up to F and then F to G? And just
We should have picked that earlier if it was through F. from F, we should have gone, which one is it? B?
So B to E, then to F, then to G. Can we do that?
No, well, we can't do it now, but then there's a mistake. Well, E is 2, right? E is, how does E reach G?
Through F.
Oh, through F, yeah, that's fine. Now, that's right, yeah. Sorry, I shouldn't be following it there. I should have looked at this, right? So E now, where is it? Which one are we calculating? B? B. B to E is 1 plus this number here, which is 3. Sorry, thank you. I was testing you, actually. So this is a 3F. That's 3F. 3, not F, 3E. It has to go through E in order to reach. E will bring us to F. Okay. The next one is C. C is going through E, goes 3 plus 2, that's 5, total 5. We already have 4, so we leave the 4D. This one, A, is not linked directly to E, and therefore we leave whatever value it has, 3D. Now, out of these here, we have 2 3s. We pick whichever one of them, A or B.
A.
Let's go for A. Okay. So we bring 3D here, and there it is. Now, either a B or a C. Well, no, from A, it has 2 neighbors, B and C, that have not been done. If we get from B, it's 4 to A plus 3 is 7, but B already has 3, so we leave the 3, better than 7. What about C? To go from C to A, it's 1 plus 3 is 4. That's already 4, so we leave the old 4. So the best next of those here is the B, which has 3 or 3 what? 3E, thank you. And that's B. And that leaves us with 1 neighbor from B, that's E. To bring 1 plus 3 is 4. We already have 4D, so we leave the 4D. And we bring the 4D as being the best machine now for C. So now the shortest route from any location. Usually it'd be asked, okay, what's the shortest route from A to G? It's the way to work it. You say, I go to A, and that will send me to D. Then I go to D, it'll send me to G. So it's A, D, G is the shortest route, and that's 3. What's the shortest route from, say, C? You go to C, bring it to D. You go to D, bring it to G. So C, D, G. And that's total of 4, and so on. So that's Dijkstra's algorithm in finding out the shortest route to any location. What time is it now? Right. I'm gonna give a quick solution to one last problem. No stopping, I'm just flying through it. If you've already seen it, that's fine. So which one is this? We're gonna work out at Hamming code. Let's imagine you got the following number. The following frame was received. 1 0 1 1 1 1 0 1 0 2 4 6 8 10 11. Does this have any error? I don't know. So let's find out. You've just received this frame. Okay, A good thing to do is to number them, sequence number them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now you should know, and maybe you will let me know, down at the very end there, in the very corner, okay, where are the parity bits here? No, not you, you're thankfully, so. Where are the parity bits? This is Hamming code, this frame is received. Eventually, we're gonna get rid of the parity bits if everything is okay. Where are the parity bits, do you know? Yeah? Location, where is the location of the parity bit from 1 to 11? 1, 2, 4 and 8. The powers of 2. 1, 2, 4, 8, 16 is always the parity. They're not part of the user data. So later on, when we find out whether there's an error or not, and if there is, we correct it, then we want to extract the user data. That means get rid of the parity bits. So these are the parity bits we will get rid of. But first, in order to find out, we're gonna find out if there is any error with any of the parity groups. We start with parity 1, parity 2, parity 4, parity 8. Parity 1 has a number of bits associated with it. Which bits? Do you remember? Which of these bits are linked with parity 1? Start with number 1. For parity 1, start with number 1, take this one, skip 1, take the next one, number 3, take 4, take 5, skip 6, take 7, skip 8, take 9, and so on. So basically, you start at number 1 with parity 1, take 1, skip 1, take 1, skip 1. Right, and then you count how many, right, you will be told in the example, if this is, say, an even or parity. Let's say this is an even. So we count 1, 2, 3, 4, they are even. That's good, there's no error here. Let's go with parity number 2. What group of bits are associated with parity 2? Do you know? Yeah? So we start with 2. I've taken 2. Take 3. Skip 4 and 5. Take the next 2, 6 and 7. Takes 8. Skip 8 and 9. Take 11. 10 and 11. That's fine. And are they even or odd? Odd. So there are 3. There is an error. With parity 2, there is an error. Right. Okay, that gentleman at the very end there. Parity 4. We start at number 4. We take the 4th bit. Skip the 5th bit. I start at number 4. Now we're dealing with parity 4. We start at number 4. We take 4 and we skip 4. So I've taken the first 4, skipped 1, 2, 3, 4, and that's it. And how many ones are they? Odd or even? Odd. There's another problem with number 2. So we have a problem with parity 2, a problem with parity 4. Now, parity 8. Start with number 8, which is 1.
Yeah.
Skip take. Okay, there's 2 here.
Yeah.
Right? That's perfect. So now we have a problem with 2 of the groups, 2 and 4. Parity 2 and parity 4. So we say 2 plus 4. Don't count how many bits they have, not because this one has 3 and that one has 3, but that's not how many bits. Which parity bits has the problem? Number 2 and number 4, then we add 2 plus 4 equals 6. What does that mean? That means there is an error with the 6th bit. So that's bit number 6. That's the one with the error. So now we're gonna fix that and we're gonna get rid of the parity bits. So now I'd fix it here. First, I fix them all. So it's 1, 0, 1, 1, 1, and instead of this one is a 0, this is fixed, and the rest of them as they are, 1, 0, 0, 1. Now extract the data. That means forget about the parity bits. That's a parity, that's a parity. Number 4 is a parity, and number 8 is a parity. So we just take this 1 and those 2 zeros, and that's zeros, and that 1, and this is the end of the problem. So I got rid of the parity bits. Oh, sorry, what's happening here? Okay, is that clear enough? Thank you very much, guys. Good luck tomorrow. You know that we have, the room is changed. Okay, you'll be notified that tomorrow's room is not gonna be AF 104. Is that where we're supposed to be? It's gonna be, I think it's gonna be 101, I think. Or 103? You got an email? Okay. Just as an extra reminder, yeah? The previous one? Okay. Right, I thought I did. I did not. I'll do it. Thank you. I'll place last year's class test upon request.